Hello everyone, this is Asra Sultana, Assistant Professor in EEE Department, working in ISL Engineering College. So in the subject of electrical machines too, I am taking for third year students. Today I am going to say about the parallel operation of alternators, and we are going to say about the synchronization of alternators and what are the requirements for parallel operation, what are the conditions for proper synchronization, okay, and load sharing between the alternators. So let us start with the parallel operation of alternator. So in power systems, whether it is DC or AC, power will be supplied from several small units or generators which will be operating in parallel, and this is advantages um, in so many ways why we have to operate the alternators in parallel. Okay, they are not operating as a single large unit, but they are operating in parallel, and they can be capable of taking care of maximum peak loads if they are operating in parallel. Okay, so there will be many reasons for the generators to operate in parallel, it will be cheaper to install one or two large units to take care of the system load, etc. The demand for the electrical energy will be always there. Okay, it will be always there, and it will grow also at a steady pace. Electrical utilities and others find it necessary to increase the generating capacity at regular intervals. So it is not economical to discard the serviceable alternator or alternators in favor of larger ones. So it will become necessary to either operate alternators in parallel or subdivide the load and feed it from multiple isolated systems. So out of these two, out of these two, parallel operation will be more preferred than operating many single units at different times. Okay, so parallel operation is much preferred because it will not require major changes in the existing system, and it will provide greater reliability. It will improve the efficiency, and it will facilitate repairs and maintenance and makes the supply of load possible when it will exceed the capacity of the largest single unit available. So what are the major things, major advantages of parallel operation is that uh, so efficiency will be increased, reliability or continuity of service is provided with the help of parallel operation, maintenance and repair will be easier, and physical size, that is instead of operating many in different units, we are paralleling all the alternators and making it as one unit. Okay, so in alternator, EMF will be induced in the stator, that is stationary part, with the influence of rotating magnetic field. Rotating magnetic field will be produced in rotor. Okay, so EMF will be induced in the stator with the influence of rotating magnetic field according to Faraday's law of electromagnetic induction. Due to synchronous speed of rotation of field poles, it is also known as synchronous generator. When the AC power systems are interconnected for efficiency, alternators should also have been connected in parallel. There will be more than two alternators connected in parallel in generating stations. Now, this is a very important question here. Can be asked for 2 marks, 2 marks, or sometimes it can be asked for 5 marks also. That what is the condition for parallel operation of alternator? Okay, in 2 marks you may also expect a question of advantages of connecting synchronous generators in parallel. Okay, so we have to know the advantages of parallel operation of alternator. We have to know the condition for parallel operation of alternators. So let us see the condition for parallel operation of alternator. So there are some conditions to be satisfied for parallel operation of alternator. So we have to understand some terms before we actually see what are the conditions. Okay. So the process of connecting two alternators or an alternator and infinite bus bar system in parallel is known as synchronizing. Running machine is the machine which carries the load, and incoming machine is the alternator or machine which has to be connected in parallel with the system. Okay, we have to know these terms: synchronizing, what is a running machine, what is incoming machine. So what are the condition to be satisfied? Let us see now. The phase sequence of the incoming machine voltage and the bus bar voltage should be identical. Okay, and RMS line voltage of the bus bar or already running machine and incoming machine should be same. Phase angle of the two systems should be equal. Frequency of two terminal voltages, that is incoming machine and the bus bar voltages, should be nearly same. The frequency of incoming machine voltage and the bus bar voltage should be nearly same. Large power transients will occur when frequencies are not nearly equal. So if these conditions are not satisfied, then it will result in the formation of power surges and current. It also will result in unwanted electromechanical oscillation of rotor, which will lead to the damage of equipment. Now, this figure showing two generators, generator 1 and 2. Generator 1 is a running machine, 2 is an incoming machine, and they are connected to a load. Okay, so the figure is showing the generator 2 is parallel with the running power system generator 1. These two machines are about to synchronize for supplying power to a load. Generator 2 is about to parallel with the help of switch S1. See, this is the general procedure for paralleling alternators. Okay, we are discussing here only about the procedure how we can connect two generators in parallel. Okay, so these two are connected in parallel. Switch should never be closed without satisfying the above conditions. Okay, conditions for parallel operation to be satisfied before we switch on the switch. Okay, so these two generators, they are connected in parallel and connected to a load. Generator 1 is a running machine, generator 2 is the incoming machine. To make the terminal voltage equal is one condition. That this can be done by adjusting the terminal voltage of incoming machine by changing the field current and making it equal to the line voltage of running system using voltmeters. So there are two methods to check the phase sequence of the machines. They are, first one is using a synchroscope. It is not actually checking the phase sequence, but it is used to measure the difference in phase angles. Okay. Second method is three lamp method. We can see here three light bulbs are connected here. Okay, one, two, three. Three light bulbs are connected to the terminals of the switch S1. Bulb will become bright if the phase difference is large, and bulbs will become dim if the phase difference is small. So bulbs will show dim and bright all together if phase sequence is the same. Bulbs will get bright in the progression if the phase sequence is opposite, and this phase sequence can be made equal by swapping the connections on any two phases of the generators, of any one of the generator. So what we are telling here, bulbs will be showing dim and bright all together if phase sequence is same, and they will be bright in progression if the phase sequence is opposite, and they can be made equal by swapping the connections on any two phases of one of the generators. So we have to check and verify the incoming and running system frequency. It should nearly be the same. So first we have checked the phase sequence. Now we have to check the incoming and running system frequency. So this can be done by inspecting the frequency of dimming and brightening of lamps. When the frequencies are nearly equal, two voltages, that is incoming alternator and running system, will alter the phase gradually. These changes can be observed and the switch S1 can be made closed when the phase angles are equal. So whenever there is a maintenance or inspection, one machine can be taken out from service and other alternators can keep up for the continuity of supply. Load supply can be increased, and during light loads more than one alternator can be shut down while the other will operate nearly full load. High efficiency and the operating cost will be reduced. These are the advantages of parallel operation of alternators. This can be asked for short questions, 2 marks. Okay, what are the advantages of parallel operation and what are the conditions to be satisfied for parallel operation? Okay, So we are continuing with the advantages of parallel operation. It will ensure the protection of supply and enables cost-effective generation. Generation cost will be reduced. Breaking down of generator does not cause any interruption in the supply. Okay, so this is the very major advantage of parallel operation. That is, if one of the generator is breaking down, the supply will not be stopped there. Okay, because other generators are there in parallel with the connection. So if one of them fails, then supply will be continuous only. It will not get interrupted. Okay. So cost is also reduced. That is very important term. The thing that cost of the entire generation will be reduced and reliability of whole power system will increase. Protection of the supply enables cost effective generation. Okay. Next we will see the synchronization of alternators. So changing from one unit to another or connecting an additional unit in parallel with the others will be carried out with the minimum possible disturbance to the existing system. So process of connecting an alternator in parallel with another alternator or with common bus bar is called as synchronization. Okay, we can connect two alternators in parallel or connect an alternator with a common bus bar. So what is the bus bar? Bus bar is the one to which various number of alternators are already connected. Okay. So conditions for proper synchronization. Uh, so So terminal voltage of incoming machine must be exactly equal to that of others. Speed of incoming machine must be such that its frequency equals busbar frequency, and phase of the incoming machine voltage must be same as that of the busbar voltage. That is, phase voltages of incoming machine and the busbar should be in phase opposition. So synchronization is of two types. First one is synchronization of single phase alternator and second one is synchronization of three phase alternator. So three phase alternator again we can see two methods, three dark lamp method and two bright and one dark lamp method. So this is a diagram showing synchronization of single phase alternator. So before connecting an alternator to the bus bar or in parallel with another alternator, so three conditions, that is that these three conditions which already we discussed, na, that is terminal voltage of incoming machine must be exactly equal to that of others, uh, and the speed of the incoming machine must be such that its frequency equals the busbar frequency, and third is uh, the phase of the incoming machine voltage must be same as that of the busbar voltage. That is the phase voltages of incoming machine and the bus bar should be in phase opposition. Okay, these three conditions to be satisfied before we synchronize the three single phase alternators. So equality of the terminal voltages can be determined by connecting a voltmeter first to the running alternator or bus bars and then to the incoming alternator. Okay, first we are connecting the voltmeter to the running alternator and then to the incoming alternator. Remaining two conditions, that is equality of frequency and phasing out, can be determined with the help of two lamps which are connected across the ends of the double pole paralleling switch, and it is known as synchronizing lamps. Okay. So let alternator B is to be connected to bus bars to which alternator 1A is already connected. So prime mover of alternator B is started and brought up close to the rated speed. Alternator is then excited and its voltage will be raised by increasing its excitation to that of bus bars or running alternator. Synchronizing lamps L1 and L2 will be connected across the double pole paralleling switch of incoming alternator B. If the frequencies of alternators A and B are exactly same and their terminal voltages with respect to local series circuit are in exact phase opposition, then no resultant voltage will act across the lamps L1 and L2 and therefore these lamps will remain dark. If the frequencies of A and B alternators are not equal, the phase angle between their voltages will be continuously changing and therefore current through the synchronizing lamps and through the local series circuit will be changing, resulting in flickering of lamps. So frequency of flickering of lamps will be equal to difference of frequencies of two alternators. That is, greater the difference in frequencies, greater will be the frequency of flickering, and lesser the difference in frequencies, lesser will be the frequency of flickering. So in the middle of the dark period, the two voltages will be in phase opposition with respect to the local series circuit. Synchronizing is done in the middle of the dark period. This is known as dark lamp method. So in the exam, you may get a question. Uh, what are the explain the different methods of synchronization of alternators? You may expect this question for large, for long answer. That is A bit or B bit, it can be asked. That is for 5 marks. If it is 10 marks question, it can be asked for 5 marks. Or if it is a 15 marks, then it can be asked for 7 or 8 marks. Okay. What are the different methods of synchronization of alternators? Okay. So synchronization of single phase alternators we have studied. Now let us see the synchronization of three phase alternators. So again in this synchronization of three phase alternators, we are having two methods. That is three dark lamp method, and second one is two bright and one dark lamp method. So additional condition which is met in the case of synchronization of three phase alternator, apart from what we have seen in for single phase alternator, is that phase sequence of incoming machine should match with that of the system to which it is going to be connected. So the process of checking the phase sequence and getting it corrected is known as phasing out of the alternator. So different methods of phasing out of alternator will be the three dark lamp method and two bright and one dark lamp method. Now let us see the three dark lamp method. So in this figure we can see that alternator A is supplying a load with alternator B and it is ready to start. If these are low voltage alternators, alternator B can be phased out by connecting three lamps across the ends of the triple pole paralleling switch. Okay, like this. These are the triple pole switch, triple pole. The prime mover of the incoming alternator B will be started and brought up close to the rated speed. Then alternator is then excited and its voltage is raised by increasing the excitation to that of the running alternator or bus bars, and the lamps will be watched closely. If the incoming alternator B is properly connected, all the three lamps should become bright and dim together. If they bright and dim in sequence, it shows that alternator B is not properly connected with bus bars and the phase sequence of incoming alternator B will be reversed relative to the system. So to interchange this, any two of the leads on either the alternator side or the line side of the switch will be carried out. So we can get the same effect by reversing the direction of rotation of alternator. So once this alternator B is properly phased out, it will always be correct until and unless either the wiring or the rotation is altered. So establishing a proper phase sequence is not a continual part of synchronizing process of alternators. So speed of the prime mover of incoming machine will be further adjusted until the lamps flicker at a very low rate, and the voltage of the incoming machine is again adjusted and it will be made equal to that of the running generator or bus bars. And paralleling switch will be closed at the instant all the three lamps are dark. So major disadvantage of this method is that lamps will go dark at somewhat less than half their rated voltage, and so the paralleling switch might be closed when there is a considerable phase difference between the machines with a high circulating current resulting in possible damage to the machine. So another disadvantage is that the lamp filaments might burn out. For this reason, it is desirable to have two frequencies which are nearly equal so that the synchronizing is not dependent on a constant dark period. So third major disadvantage of this method is that the flicker of lamps will not indicate whether the incoming alternator is slow or fast. So these two difficulties can be overcome by using another method called as two bright and one dark lamp method, in which two of the lamps are cross connected. So when the incoming alternator is in synchronism with alternator A or bus bars lamp, L1 and L3 are bright and L2 will be dark. So near the point of synchronism, light brightness of one lamp increases and of another decreases, so that the instant at which the incoming machine is in synchronism with the bus bars can be accurately determined, and paralleling switch should be closed at this instant. So let voltage star R Y be referred to bus bars and bus star shown in dotted, that is R dash Y dash B dash to incoming machine C. So instantaneous voltage across three lines will be given by phasors R Y dash, R Y dash, R dash Y and B B dash. Okay, as we can see in this figure, R Y dash, R dash Y, R dash Y and B B dash. So when the frequency of incoming alternator will be same as that of the bus bar, both phasor diagrams will rotate in space with same angular velocity. So the potential difference across the each lamp will remain constant. If the incoming machine is too fast, then phasor diagram R dash Y dash B dash will rotate faster than RYB, so that the voltage across lamp L3, which is represented by RY dash, will decrease, and voltage across lamp L1, which is represented by R dash Y, will increase, and voltage across lamp L2, represented by BB dash, will decrease. Okay. So what we are telling here? If incoming machine is fast and phasor diagram R dash Y dash B dash will rotate faster than R by B, so voltage across L3 decreases and voltage across L1 increases, L2 decreases. And if the incoming machine is too slow, then R dash Y dash B dash will rotate slower than R by B. So that at that instant voltage across L3 increases, voltage across L1 decreases and voltage across L2 increases. So hence when the three lamps are placed in a ring, a light wave traveling in counterclockwise direction or anticlockwise direction indicates that the incoming machine is slow, and light wave traveling in clockwise direction indicates that incoming machine is fast. So by observing the sequences of brightness of the lamps, it can be determined whether the machine is moving slow or fast. So paneling switch will be closed when the changes in light are very slow and very slow, and at the instant the lamp L2 is connected directly across one face is dark. In case of high voltage generators, which is the usual case, direct connection of lamps is not practical. In such cases, lamps may be connected through potential transformers. So what are these potential transformers doing here? Potential transformers will directly connected across the switch and the lamps into the secondary circuits of the potential transformers. But most installation there will be a potential transformers connected across the line on both sides of the paneling switch. Another method of synchronizing is that with the help of one three-limbed transformer and a lamp, the two primary windings on the outer limbs connected to the bus bars and the incoming alternator respectively, and secondary winding on the central limb, like this. Correct moment for closing the paneling switch is the middle of the dark period if the primaries are each connected same way around, and the middle of the bright period if the connections of one winding are reversed. If phase sequence is known to be correct, the best method of synchronizing alternators is by means of a single phase device called as synchroscope, which will provide a more accurate indication of synchronism than lamps. Okay. So synchroscope is an instrument for indicating difference of phase and frequency between two voltages. It is a split phase motor in which torque is developed if the frequencies of the two voltages will differ. Voltages from corresponding phases of the incoming and running generators are applied to the synchroscope. So a pointer which is attached to the rotating part of the instrument moves over the dial face in either clockwise or anti-clockwise direction depending on whether the incoming machine is fast or slow. When the frequencies of two alternators are equal, no torque is exerted on the rotating part of instrument, and so the pointer will stop. So when the pointer stops in vertical position, frequencies are equal. The voltages are in phase and the paneling switch may be closed. So, but in practical way, it is very difficult to adjust the speed of the incoming machine closely enough to stop the synchroscope pointer in vertical position. So in that case, speed of the incoming machine should be adjusted as closely as possible and paneling switch closed just before the pointer reaches the vertical position when traveling in the fast direction. So now let us see the terms synchronizing current, synchronizing power, synchronizing torque. Okay. So once a synchronous machine is synchronized, it will tend to remain in synchronism with the other alternators. Any tendency to depart from the condition of synchronism is opposed by a synchronizing torque, which will be produced due to circulating current flowing through the alternators. So when two alternators are exact in synchronism, the two alternators will have equal induced EMFs which are in exact phase opposition. No circulating current will flow around the local circuit. When the EMFs induced in the of two alternators are equal in magnitude, but they are not in exact phase opposition, the resultant EMF will act around the local circuit and causes flow of current called as synchronizing current. If any alternator due to some disturbance tends to retard, the EMF induced will be falling back by a phase angle delta. So, though their EMFs induced, that is E1 and E2, are equal in magnitude but have a phase difference of 180 degrees minus delta. Okay. So, resultant EMF will be 2, ER will be equal to 2E cos 180 minus delta by 2, that is 2E sin delta by 2. Synchronizing current will be given by ER by ZS, that is E delta by ZS. ZS is the combined synchronous impedance per phase of two alternators. Synchronizing current will lag behind the resultant EMF by an angle theta. That will be tan inverse of XS by RE. XS is the combined synchronous reactance and RE is the effective resistance of the two alternators. Now let us see the synchronizing power. So synchronizing current we have seen, now we will see the synchronizing power. So when machine 1 will supply power equal to E1 ISY cos phi 1 and machine 2 receives the power equal to E2 ISY cos 180 minus phi 2. Power supplied by machine 1 will be equal to power supplied to machine 2 plus copper losses. So power supplied by machine 1 is called synchronizing power. So synchronizing power will be given by the formula E1 ISY cos phi 1, that is delta E square by XS. And total synchronizing power for three phases will be equal to 3 delta E square by XS. Okay. So now let us see the synchronizing torque. Synchronizing torque will be equal to, that is P is equal to T into omega. So the 3 PSY equal to TSY into 2 pi NS by 60. Or synchronizing torque is equal to 3 delta E square by 2 pi NS XS, where NS is the synchronous speed equal to 120 F by P. So sharing of load when two alternators are in parallel, when several alternators are required to run in parallel, it will probably happen that their rated outputs will differ. In such cases, it is usual to divide the total load between them in such a way that each alternator takes the load in the same proportion of its rated load in total rated outputs. So whenever we are making several alternators to run in parallel, their rated output will differ. So in such cases, it is usual to divide the total load between them in such a way that same proportion rated load we are dividing into the alternators. So total load is not divided equally. It may be desired to run one large alternator permanently on full load and fluctuations in load being borne by one or more of the alternators. If the alternators are sharing the load equally, then these are the power triangles. Okay, this is the power triangle where we can see y-axis here, it is load in kilowatt, load in kVAR, kilovolt ampere reactive. Okay, this is kilowatt, this is kilovolt ampere reactive, and this is kVA. Okay, this is machine 1 and machine 2. And this is another phasor diagram showing load is shared between two machines, that is kilowatt 1, load kilowatt 2, and this is load kVAR 1, load kVAR 2, load kVA 1, load kVA 2. This is machine 1, machine 2. So what we are telling here, that whenever we are making several alternators to run in parallel, so their outputs may differ. So what we are doing here, we are dividing the total load between them in such a way that each alternator will take the load in same proportion of its local load. It will adjust itself to the load and output. Okay. So let us consider two alternators with identical speed load characteristics connected in parallel. Okay, two alternators are connected in parallel. We can see in this diagram. Okay. Let E1 and E2 be the induced EMF per phase, Z1 and Z2 be the impedances per phase, I1, I2 be the current supplied by each machine per phase, and Z is the load impedance per phase, V is the terminal voltage per phase. So from the circuit diagram, okay, from this we can write V is equal to EI minus IZ, that is equal to E2 minus I2 Z2, and hence I1 equal to E1 minus V by Z1, I2 equal to E2 minus V by Z2. So we are applying the KVL to the loop and KVL and KCL, and we are writing the equations for voltages and currents here. V1 is E1 minus I1 Z1. V is equal to E1 minus I1 Z1. Also V is equal to E2 minus I2 Z2. So I1 will be equal to E1 minus V by Z1 and I2 equal to E2 minus V by Z2. From this equation only we are taking the equation for I1 and I2. So V is equal to I1 plus I2 into Z. Okay. So IZ we are writing. I1 equal to E1 minus E2 into Z plus E1 Z2 by Z into Z1 plus Z2 plus Z1 Z2. Similarly, we can write the equation for I2. So total current is the addition of these two currents I1 and I2. So I am writing the equation of total current I is equal to E1 Z2 plus E2 Z1 by Z2 into Z1 plus Z2 plus Z1 Z2, and the circulating current or synchronizing current is given by E1 minus E2 by Z1 plus Z2. Thank you everyone for watching the video. So with this we have finished the third unit of electrical machines to subject. So in the next class I am going to start the fourth unit. I hope everyone is clear with all the topics of third unit, 1, 2, 3 units. If you have any doubts, you can ask me anytime, students. And I have given you 3 assignments also. For each unit, I have given 1 assignment to you. Okay. So that is tomorrow. That is on 12th. Is the last day to submit your assignments. All the students should submit the assignment by tomorrow. Okay. Thank you, students, for watching the video.